Welcome to this lecture on signal flow graph. This is our third tool. We have said that we will introduce three main tools of microwave engineers in this course. The first was Smith chart, the second was scattering parameter, the third is signal flow graph. Now, what is a signal flow graph? It is I think many of you have used this in your study of control theory. We have used signal flow graph, where if you have a block diagram and various blocks they have some interrelationship. If you want to find the transfer function of the whole thing, that means any linear network if you are having, and you know that various branches etcetera they are connected, that there is some interrelationship between various blocks, then what is the overall transfer function that you can find here. The same thing here, we see that if we know the wave is propagating in various ways between various parts of a circuit. Now, from one part to another part, if we want to find the transfer function or the gain, then this signal flow graph is very much needed. And in our case, we will see that when a network gets very much complicated, like we will see the network analyzers calibration procedure, there the network is quite complicated, but that time if we know signal flow graph, we can very easily find out the things. Similarly, in various microwave characterization, particularly for amplifiers etcetera, we have various power gain definitions. Now, that sometimes create a lot of problems if we do not use this tool of signal flow graph, but signal flow graph can very easily, very elegantly help us in such cases to find the gain or transfer function of between one part of network to another part. But you know that as in case of Smith chart or scattering parameters, we have seen that if we want to use a tool, we need to learn its rules, because under certain rules this whole thing becomes elegant. If we do not follow those rules, then the elegancy turns to be a blackmail. So, that is why these rules are introduced here, that each variable, that means variable means in a network you have seen that it can be either V1 plus or V2 plus or V1 minus. So, those are designated as a node in a signal flow graph. The S parameters and reflection coefficients are represented by branches. So, S parameters, any S parameter there or reflection coefficient there, they should be represented by a branch. Branches enter a dependent variable node and emanate from independent variable nodes. So, obviously, branches can enter a dependent variable node and an independent variable node that makes that it behaves as a source of the wave etcetera. Independent variable nodes are the incident waves. So, you see that which are incident, that means the excitation waves or coming from the source the waves, they are the independent variables. And obviously, depending on the network's behavior, you get a reflected wave, that is a dependent variable node. Value of a node is equal to the sum of the values of the branches entering it. So, you see that you see here, instead of now to, since there are other things involved. So, instead of V1 plus, V1 minus etcetera, here any plus quantity is called as A and minus quantities are called as B. So, basically you can think that this is your V 1 plus, this is your V 1 minus. Now, in a two port network, how V 1 minus comes? If you see this thing, that in our two port network, I have V 1 plus, I have V 1 minus, I have V 2 plus, I have V 2 minus. Now, how V 1 plus comes? V 1 minus, due to this V 1 plus I can get some V 1 minus, that we call as S 11 V 1 plus, plus due to this V 2 plus also I can get a V 1 minus, that we call as S 12 V 2 plus. So, V 1 minus, that is the B 1 here. So, from A 1 this V 1 plus I am getting S 11, that is why S 11 A 1. From A 2, that means V 2 plus I am getting S 12. So, this is the representation of B 1. As the last rule said, that value of this node is sum of the branch values that are coming here. Now, branch value, this branch S 11, A 1 into S 11 plus A 2 into S 12 will be B 1. So, these two are entering. If another was entering, another plus would have been there. Similarly, the dependent variable in the second port B 2, which was actually V 2 minus, that we can write as V 2 minus is equal to S 21 V 1 plus plus S 22 V 2 plus. That has been done. So, finally, we can combine the two ports, that in the port 1 I have V 1 plus V 1 minus. So, A 1 B 1, in the port 2 I have B 2 A 2. Now, it is done elegantly that B 2 has been placed here instead of putting it here. So, that you can get a very A 1 to B 2 what is going is S 21, A 1 to B 1 what is coming is S 11. Similarly, from B 2, from A 2 you are getting whatever to B 2, that is S 22, and A 2 whatever you are getting here is S 12. So, a two port can be represented in a signal flow graph with its S parameters as this. So, this is a two port representation of a two port representation, two port network with its S parameter can be represented in the signal flow graph like this. Similarly, you see block diagram of a generator. So, we know that V g, the total voltage, that is open circuit voltage you are getting, that will be E s plus I g into G s. Now, V g you can break into again two parts, that V g plus and V g minus. V g plus you call A g and V g minus you call B g. So, that again is written here, and by solving, this is the generator, that you are having a B s, from that you are getting B g, and in A g you are putting that value, that reflection coefficient of the source, that is coming as gamma s. Similarly, signal flow graph of load impedance is load, there is one incident, one reflected wave. So, their relationship is the load reflection coefficient. Now, so two port network loaded, and you can say generated two port network or source two port network. So, you have the here there will be a source between the network and the source, there is a reflection coefficient gamma s, there is a load reflection coefficient gamma L. So, this is the complete network. You know that sometimes we find the S parameters after finding given a particular load impedance and source impedance, we want to find what are the various values. So, that time this network is used. Now, there are some terminologies in the signal flow graph. The first thing is called first order loop. Its symbol is L1. Now, what is a loop? Loop means any branch or a combination of branches which are starting from a node and making a round trip and coming back to the same node. Now, that is why the path starting and ending on the same node. It may be a single branch, that is called self loop. It may be various branches, after that it is coming back, that is a standard loop. This first order loop, why it is called first order? That means that any loop you find that we will call a first order loop. Then there is second order loop. Second order loop is product of any two non-touching first order loop. First we have seen loops, all loops we are calling in general first order loop. Now, out of that second order loop means two product of any two non-touching first order loop. So, we will have to identify who are touching. If they are touching, they are rejected, but if they are non-touching two loops, then their product is one second order loop. All these pairs we will have to identify and find. Then we have third order loop. So, product of three non-touching first order loops. Like that you can go on any order. So, in a network, as it gets more and more complicated, first you will have to identify the loops, then that means you have identified all the first order loops, then you find out what are the non-touching pairs of loops, those are second order loops, then you identify the triplet of non-touching loops, that is third order loop, then you identify quadruple of first order loops, non-touching first order loops, that is called L4, etc., etc. Now, you see this is L1 with a superscript P. L1 is the first order loop with a superscript P, means first order loop not touching path P. So, there can be several paths in which we are interested, and L1 P1 is first order loop not touching path P1, L1 P2 first order loop not touching path P2, etc. Similarly, L2 P second order loop not touching path P, etc. Now, this is the formula. I think this formula many of you have used in the control theory. In electrical control, this is used. Many type of block diagram, when we try to find the transfer function from that, generally this formula is used. It is well known, Mason's formula. Generally, we call that gain, that means some dependent variable by some independent variable. As we have said that dependent variables are the reflected type of thing in our microwave things, and independent things are our incident things. So, one dependent variable, that means some reflected by some incident, that we are calling gain. It may be gain, it may be anything. Basically, it is a transfer function. Now, that is written by this formula. You see that what is this formula says, that you find out P. Now, there can be several paths from this independent variable that you are interested to the dependent variable. Suppose A1 and B3. So, between A1 is a node, B3 is a node, A1 is an independent node, B3 is an dependent node. you come from that independent node to dependent node. See how many paths you can come like that, those are your paths. They are called here, you see P1, P2, P3, etc. Now, you find out what are L1s, how many first order loops are there, that means how many standard loops are there. Now, sigma L1 means sum of all first order loops. Then you identify second order loops, sum of all those second order loops. Then sigma L3, sum of all three third order loops, etc. And in the numerator you see this path will have some value means the reflection coefficients, etc. on that path. Each branch will have some reflection coefficient or some S parameters. So, that product of that, so that path value multiplied by 1 minus this L11. L11 means all first order loops which are not touching path 1, sigma of that. So, there may be several such. Similarly, all second order loops not touching path 1, all third order loops not touching path 1, all fourth order loops not touching path 1, etc. And the sign you see minus, plus, like that. Then path 1 is closed. Then repeat that for path 2. So, again 1 minus this L12 means all first order loops not touching path 2. Then L22 all second order loops not touching path 2, etc. So, this will be the numerator. So, this will give you the value. Now, you need some time to get it inside you, that this terminology, but with examples we will try to tell you. And P1, P2, I am again repeating what is P1, P2, various paths connecting the independent variable to the dependent variable of your interest, because there may be several dependent and independent variables in that. All dependent variables will be B something, B subscript, and all independent variables are A subscript. You are going from one independent variable to one dependent variable. And path, set of consecutive co-directional branches along which no node is traversed more than once as moved from independent to dependent variable. This is important, that you can take any path from going to the independent variable to dependent variable, but no two paths, no two nodes should be traversed twice. That means, it should be completely a different path. That means, through a loop you cannot come to anyone always, because if you traverse through a loop, basically you are traversing the node twice. So, paths cannot contain any loops. Path value, product of branch values in the path. Now, let us take this example, that suppose we want to find B1 by Bs. Now, here you cannot find B1 Bs, B1 Bs, okay. So, from here, though it is written as Bs, actually it is As, because it is an incident thing. So, from here to here I want to find what are the paths. You see, one path is here, then this one is one direct path, that is why let us call this as P1 is S11, and also I can come here, then I can go here, then I can come here, I can come here. So, this is another path P2, it is 1 into S21 into gamma L into S12. You see, there are no other paths here. This is a path, but this is not a path because arrow is not here. I will have to come here, and this one I cannot take. So, only thing is this. So, there are only two paths in the network for coming from BS to B1. Now, let us first find what are the L1s, first order loops. So, while coming from here to here, what are the loops? One loop is definitely this, that we are calling S11 gamma S. Then another loop is obviously this S22 gamma L. Now, there is another loop here, you see I am starting here, coming here, here, this is a loop. So, S21 gamma L, S12 gamma S, S21 gamma L, S12 gamma S. See, no other loops are there, first order loops are there. So, there are three first order loops. That means, when we will sum in the denominator, you see sigma L1, that will be sum of three loops. So, that will be S11 gamma S plus S21 this plus gamma L S22. Now, the same thing, is there any second order loop? That means, are there two loops which are not touching? You see, this is one loop, but that is touching with this, touching with this loop. So, this one and this one, they are not non-touching, but this one and this one is non-touching, this one and this one. So, there is one second order loop. So, that is called S11 gamma S and S22 gamma L, they do not touch. So, we will write L2 is, there is one second order loop, and that loop value is product of these two. So, S11 gamma S into S22 gamma L. Now, we have seen there are two paths. Now, L1P. So, L11, L12. Now, L11. Now, there are three L1s, as you have seen that this is one L1, this is another L1 and this is another L1. There are three first order loops, but which one is non-touching to path 1? What is path 1? This path. This was our path 1. Now, first loop and this loop, they are non-touching, means that they do not share any common node. So, first two loops, they do share common nodes with this path, but this one does not share any common node with this one. So, this one is a non-touching loop. So, L11, that is why we are writing gamma L S22. And is there any first order loop which is non-touching with the second path? What was our second path? This to this. Now, you see all the loops are touching this path. So, L12 is equal to 0, and among these three loops, is there any triplet of non-touching loops? No. So, no third order loops in this figure. Then second order loop we have already seen, but is there any second order loop? What is the second order loop? This one and this one, not touching path 1, but it touches path 1. So, that is why we have written L21 is 0. Similarly, this second order loop that touches path 2 also, this is path 2, it touches that. That is why L21 is equal to 0, L22 is equal to 0, and no third order loops in this figure. So, in Mason's gain formula, we can put all that. We have written here P1 value, we have written P2 value we have written, L1 we have written the 3 loops, 3 first order loops, second order loop, 1 second order loop, no third order loop, L11 is only existing, L12 is not there, L21, L22 is not there. So, you can write this will be the that transfer function B1 by Bs. So, for this one, if you want to find B1 by Bs, this will be the value. Now, let us come to our one point, that suppose I want to find the input reflection coefficient of a loaded circuit. This part is the S parameter part up to this. Now, there is a load. So, there is a load reflection coefficient. Now, from here if I want to loop, what will be the value? So, you see that what is my P1? P1 is, that means I am coming from, you see, B1 by A1, that means this is independent variable, this is dependent variable. So, how I can come from A1 to B1? One path is this, we are calling it P1, that is S11. Another path is I can come here, I can come here, I can come here. So, P2 is S21 gamma L S12. Now, is there any loop? Yes, one loop is, this one is a loop. You see there are no other loops possible. So, that means only one first order loop, and so obviously L2 and L3 they are all 0, but this L11, that means first order loop, that means this loop, is it non touching with path 1? Yes. So, L11 will be this loop S22 gamma L. L12, is it non touching with this path? No. So, L12 superscript, that will be 0. So, now you put gamma in will be this. So, that you can put now the values, and this is the well known value. You see how simply we got it. In actual S parameter things we have derived that, but that requires some manipulation, but here just directly we have got this value. And when that match load, when gamma for if the load is a match load, then gamma L will be 0, and you will get that gamma in is nothing but S11, that we know, that we have discussed in scattering parameter also, that generally reflection coefficient at the input port is not equal to S11, but under second port matched you get this. Also unilateral device, that means generally a device, if there is from 2 to 1, if there is no path, then you can also get gamma in. Basically, gamma L is equal to 0. Match load makes this path 0, but there are also some devices whose S parameter is such that S12 is 0. In that case also you can get that gamma in is S11. Similarly, you can find it out from output reflection coefficient, that output reflection coefficient will be this B2 by A2, that means how you can come from A2 to B2. So, there are again if you put that one path is this, another path is go here, come here. So, then find out what is the loop. There are one loop is here, another loop is, you can say that this is another loop. So, these two loops. So, you do that and you can get these. Okay. Similarly, there are various power definitions, we are not going there. When you study amplifiers, you require that. So, I think we have completed that signal flow graph. We have seen the introduction, how to manipulate that, and later in the next lecture we will try to find out its application. Already I have shown you some application, a very important application that we have introduced you to network analyzer. So, its calibration comes easier if you do with signal flow graph, that we will see in the next lecture. Thank you.